Come on. Okay.
All right, we're back.
So great. So the as it turns out, our when we kind of present this theory, we talk about very arbitrary symbol sets and constellations and that type of thing. Oftentimes, they're very a lot simpler than it has to be, right? So theoretically, we draw out a big correlation receiver or a match filter receiver where we have all these different branches for each symbol. But as it turns out, most of the time our symbol shapes are the same. They're just scaled by an amplitude or shifted by a phase or something like that. So we can run them through a single filter and just kind of map it to different types of amplitude levels. So, all right. So, there we go. Um, that is a pretty quick exam preview. I hope that helps. And yeah, I wanted the other one. Let's go through the homework real quick. Confirm, hopefully you can see this also. So I gave you some hints on this and also decided that we wouldn't worry about problem 320, the FSK one that just got a little too hairy. So the gray code one here, in the last lecture, I kind of outlined a kind of a nice plug and chug approach to creating a gray code. And so we did the example of 2-digit to 3 digits. You basically take your existing set, you reverse it, concatenate them, add a leading digit, make that first set leading digit be 0, and on the second set, the leading digit be 1. So then just plug and chug and repeat the process, and you should end up with something like this, right? But now you still have the challenge of figuring out how to assign those to the constellation. So just start in one place, and there's some degrees of freedom, so you may not come out exactly with the same result I do, but it should still satisfy this idea that if you start in one place with the first code in that set and run out that radial arm and then step to another one, and now here this point is nearest neighbor with this one, so these 2 points have to satisfy the gray code also. And so you can do that by starting off at the 0, 1, 0, 0 and then running out that arm, radial arm, whatever. So, and continuing the process to here, making sure that now this code satisfies the gray code criteria with this one and only 1 digit changing. And then you can run out that way. And finally here, this one's got to be consistent with that constellation point and this one, right? So if you notice that in this case, these leading 2 digits on each of these are kind of our 2-digit gray code, right? So okay, so that's again, there's some degrees of freedom here, so you may come up with something different, but the key here is making sure that these guys are nearest neighbors to each other, but all of these inner ones are nearest neighbors. Okay, so all right, second problem here. Again, skipping over the FSK one. Binary digital communication system. So this is on-off signaling. Still a binary. We're still assuming they are equal probable. Keeps life simple. So here we're either off or we're on, right? So this represents a third type of binary signaling. As I said earlier, we had antipodal, where we'd have minus A and A. And then we also looked at quadrature signaling, where we would have like A times J, or 0 comma A and A comma 0 in the complex plane, right? So, and now we've got 0 comma A. So these are the more common ones. And so so how do we approach this? Well, it's a correlation receiver. I kind of gave you some hints, starting points in the lecture, that S1 is this, as a vector, is A times the square root of T. But how did I find that? As I continue to say, we've talked about basis functions. We haven't dove deep into them, for the sake of time. Maybe we should have, because they keep coming up. But we do know that they need to be orthonormal to each other. Okay. Now, when we look at this, this has one dimension, right? It's just along the x-axis. It's not along the x and y-axis. It's not any higher dimensions. It's just one dimensional. So n is equal to 1, and therefore we really only need one basis function. Okay, so so we consider the energy in this rectangular pulse. So that's going to be this A squared integrated over time, right? So that's the energy now. So we have to square the amplitude, and we integrate that. The pulse is defined, it has support from 0 to T, and it's 0 elsewhere, right? So that's given up here in these conditions out there, right? So so that produces an energy of A squared T. So we can define our basis function, phi of T, here as this 1 over the square root of T, from 0 to T, and 0 otherwise. So you can run through and see, okay, that's going to be provide an orthonormal basis function. So this is the full-blown correlation receiver. So we're taking this receive signal and we're multiplying it by these basis functions. In this case, it's much more trivial than this. But then we integrate, that produces a vector, vector R, and then we correlate it with our vectors that represent each of our symbols. Okay, and we then, if need be, in this case we don't because they're equal probable, but we add the bias term and then select it, right? So that's a generalized correlation receiver. So here we have, we can end up with this as R is equal to some symbol, S0 or S1, with noise added to it at the receiver, right? And so in this case, we know that S0 is 0, and S1 is this A times the square root of T, which I gave you. So our noise, we always use this notation N naught over 2. Okay, so now here's the key part. All right, even if we're not going into lots of detail on how you arrived at this, the key is, now what do you do with this information, right? So what we look at is that the probability of density function at this detector where we're looking at it, right, is in one case it's going to be this S, for when S0 is sent, our received vector is going to, well, its mean is 0, right? Because that symbol is sent, or essentially not sent, because it's on off keying. And in this case, you turn the transmitter off, so you're not sending any energy. And so the mean is going to be 0. So this is your Gaussian distribution with a 0 mean. Okay, and a sigma squared of n naught over 2. And but then what is it for our symbol 1? Now our energy is a times the square root of t, right? So that's going to be the mean, right? So now we have that the Gaussian distribution is usually x minus the mean divided by the sigma squared here, right? So and so here, our x, well, we're really looking at this received random variable r, right? So that's our x. This is our mean that we're subtracting, and this is that representing the sigma squared, right? So we've simplified and subbed in these, and the twos cancel out with the factors that are in the basic Gaussian formula, and similarly in this coefficient. So this is describing the expected, the probability that R, where is it going to land, right? So that's ideally it would be right at 0, but there's going to be some noise impact on that. So recall that the symbols are equal probable, so we don't need to worry about the bias term. So we're going to decide in favor of S naught if the probability of R given that S0 is greater than the probability of R given S1 was sent, right? So if that probability of R given S0 is larger than this probability of R given S1, then we decide in favor of S naught. Otherwise, we decide in favor of S1. Well, let's plug all that in and see how that works out, right? And I introduced this notation last lecture, and here we would have the probability of R given S0, right? So I'm just taking this equation up here and plugging it on the numerator, and this one plugging in on a denominator. And so at this point, if they would be equal to 1, then that would be our decision boundary, right? Because it would be kind of a toss up of whether it's one or the other, right? So but if this fraction is greater than 1, that means the numerator is larger than the denominator, or the numerator has higher probability than the denominator. I'm hand waving there, but then we would decide in favor of S0. So it's just rewriting this equation up here in my text after substituting these things in, right? So if the denominator is larger, then that would be the converse of this equation up there. And this whole quotient then would be less than 1, right? So then we would decide in favor of S1. So just recognize that notation there, right? So now we just do our algebra. These coefficients cancel out nicely, and we have a common base here in E, and so we can take this term, subtract this term. There's a minus sign out there, so we can multiply this square out and cancel out some terms. The R squareds will cancel out, and you will end up with this relationship. Okay, so now we look at this and it's like, can we simplify it some more? And yes, you can, just with some a little bit more algebra there, and noting how this is going to work out. So R, if R is greater than this, then you're going to decide in terms of S0. Now, you can do all this by inspection. Once you know that S1 is value is A times the square root of T in the vector form, and the other constellation point is 0, then draw, and they're equiprobable, then you draw the connecting line between them. That's just going to lay on the x-axis. And then you bisect that with a line that's normal to that connecting line. And bisecting means you're halfway in between, right? So that's the 1/2 A times the square root of T. But this is fundamentally how you would derive that without that handy dandy rule. All right, so now this second half requires a little bit more work too. Determine the probability of error as a function of the signal noise ratio. How does on-off signaling compare with antipodal signaling? So here we average the errors. What happens if we have an error when S0 is sent? And what happens when we have an error when S1 is sent? Well, if we're averaging them, we take half of those probabilities and individually and add them up, right? It's just a simple average. There's two terms, so we're dividing by 2. And now we plug in these probability of error, and this is the essential concept I want you to understand, right? So when error occurs, when we're on the wrong side of the decision boundary, when that probability of that noise amplitude being large enough, if you envision a Gaussian distribution around 0, then everything from minus infinity up to that threshold line is still the decision area for S0. So they're all good. It's only when we're pushed on the other side of that threshold line, the 1/2 A times square root of T, if we're to the right of that, as we conventionally draw our things, anywhere to the right of that, all the way out to positive infinity, right? So that's how we're setting up our integration limits. So we're integrating that probability. This 1/2 out front comes from this previous equation here, right? The integration limits, we're integrating that Gaussian PDF, the probability, from that threshold line out to infinity. So encompassing the wrong decision area, okay? Then we repeat it, but for S1, now for S1, the error region would be anywhere from minus infinity up to that threshold, or basically anywhere lying within decision area 0. So again, the 1/2 comes from this equation up there, and we sub in our PDFs now. So that's just direct substitution. We already wrote those out. And so then you can do a variable substitution here where we're trying to get this equation in a form that looks like when we derive the Q function. Okay, so we like this Q function because someone's already calculated tabular values for us, so we can just go look them up. So the challenge in this problem here is determine the integration limits, and then doing a little bit of variable substitution, get it to look like the Q function, right? So we want this e to the minus x squared over to dx integration. So now we've done that, and so that changes our integration limits there and there. Okay, and so then that turns out to be this Q form. You go back and look at the Q relationships when you have a Q of a minus argument. Then you see that you can add these two together, and the halves cancel out, but you end up with this type of relationship here. So so this looks like BPSK, okay, or this. So it does ask you to. Where's that? Okay. Compare it with antipodal signaling, right? So if you look up in your notes, then you will see that this is going to be a factor of 2 related in this signal noise ratio too. So to provide the same error rate with on-off keying, you need twice as much power. Okay, so your signal noise ratio needs to be twice as much. Conversely, you could reduce your noise by half, or you could, any combination, as long as the SNR is twice as much for the on-off keying, you will get the same error rate. All right. Now, let's go back to this binary BPSK, or antipodal signaling. Remember, a minus sign and a coefficient is equivalent to pi radians in the phase, right? So a binary PSK, we're usually using a pi, a 0 and pi, or plus or minus pi over 2 or something like that, right? So so suppose that the binary PSK is used for transmitting the information over AWGN channel. We're given this power spectral density of the noise, okay? Then the and transmitted signal energy here, then T is the length of our bit, and or bit intervals, and A is the signal amplitude. So yeah, how do we determine how much signal amplitude, okay, directly related to the power of the signal that we're going to send? Excuse me. And we want our we want to figure out how much signal we need to send in order to, or ultimately to receive, in order to achieve an error probability at 10 to the minus 6. And here, this lesson is to see how it changes with respect to our rate. So for BPSK, we can just use this Q function, and now you can kind of go back and look at where we're comparing this term from the previous problem, right? So and so now we were given this information inside here. So with PE, probability error equal to 10 to the minus 6, you go into the Q table and you work backwards, right? So you find what argument corresponds to 10 to the minus 6, and that's about 4.74. Okay. So that argument inside that Q function will produce this error rate of 10 to the minus 6. So if we square these terms and apply the that noise power spectral density given up here, 10 to the minus 10th, then we're going to end up with this equation here, right? So, or this value here, right? And then in that case, we have A, B, and C here. So I've just noted that the rate for A is equal to 10 kilobits per second. That's actually 10 to the fourth then. And so the reciprocal, or the period, is now 10 to the minus fourth. And so now solve for A. So we have this relationship here. We've got that value. We've got T. So divide by T and take the square root, and you should end up with this value, and just repeat the process for B and C. So what we see is, to achieve higher and higher rates, we need more and more signal. Okay, so in the case of going from A, oops, I'm sorry, these should be, I didn't fix those. So all right, so for C here, we need 10 times as much power as A. But we went from 10 kilobits all the way up to a megabit, so, or 1,000 kilobits. So we factor of 100, we needed 10 times as much amplitude. Okay. All right. Hope that makes sense to y'all. How much time do we have? We got a little bit of time. We'll just get started on band limited channels then. So yeah, we got through test preview and homework 2, and we'll just give you a taste of the channel characteristics here. So channel needs to carry the information encoded on the signals to a distant receiver, right? That's its purpose. It must also provide for the simultaneous use by many other users, right? That's not just you that wants to communicate. Everyone wants to communicate. And so we have to figure out, how do we share whatever communication media that you have. And there's a number of different ways of doing it, but kind of a most fundamental way is to allocate different parts of the radio spectrum to different users. Now, some parts of that spectrum do a good job of sending information really long ways. Other parts of the spectrum are really only useful for what we call line of sight. You got to be able to see the receiver from the transmitter, or vice versa, right? And so it doesn't account for the curvature of the earth or anything like that. So different parts of the spectrum have different pros and cons and that type of thing. And so we try to allocate spectrum in a way that makes sense, so that everyone who wants to communicate can in some level, right? And it's up to the regulatory agencies to decide who gets priority. And in a lot of cases, they auction off the spectrum. And I think I mentioned this in my intro class, but spectrum for a particular wireless carrier, let's say Verizon or AT&T or T-Mobile, they're going to spend several $billions to get nationwide spectrum, new spectrum when it's released. So spectrum's a very valuable resource. All right, what have we said about channels so far? I was gonna kind of do this as a Q&A, but I'll just rattle them off just for the sake of time here. Well, we've said that in a lot of cases, we like to treat them as this AWGN, additive white Gaussian noise. There's other channel models that you can look at that are more complex. Path length can affect the phase at the receiver. We looked at that early on. We can have multipath interference, where a signal bounces off a building or a wall or a mountain or something like that, right? Um, and so you end up with uh, two or more signals that have traveled at different distance that arrive at the receiver. And so since they have traveled a different distance with each other, they have different phase with respect to each other, and they will potentially uh, cancel each other out, or ultimately they'll add vectorially, right? So they might add together or they might cancel each other out. Most likely it'll be somewhere in between, right? Um, there's a need to fit within this allocated portion of spectrum that meets our needs, especially for transmission distance. And but also we have to deal with this channel by saying, okay, I'm going to take my little voice signal, which doesn't have very much bandwidth, a few tens of kilohertz, but I'm going to modulate it and send it at say 600 megahertz, because that's a chunk of spectrum that has been allocated to me, let's say, and it's mine. And so I can use that chunk of spectrum and know that other users might be using 601 megahertz or 602 or 599 or something like that, right? And if we all have our little chunk of spectrum, then we don't interfere with each other and we can all talk at the same time. So kind of maybe trivial, but kind of fundamental to what we're doing here, right? So some things we haven't talked about or we've only mentioned briefly, I'll toss them out here now. Doppler effects can be a big deal in mobile communications. And so we know that if our transmitter is moving or receiver is moving, or perhaps the thing that our signal reflected off of is moving, then the frequency of that signal is going to change based upon the Doppler effect. If they're getting closer together, then they're going to be raised up in frequency a little bit. Vice versa, if they're coming apart from each other, right? So definitely a big deal in mobile communications. It's a big deal in satellite communications, especially in LEO, low Earth orbit, where Starlink and that type of thing are at. And you have a big Doppler effect as that satellite orbits. It'll tend to come up over one horizon and pass over you and drop down behind the other horizon. And it'll be at first coming towards you and then going away from you. So there's a big Doppler effect. We've also mentioned some nonlinear effects, power amplifiers. There's a term called passive intermodulation distortion. You can actually get signals mixing together non-linearly because you've got some degraded insulator in an antenna where maybe it got cracked and some water intruded or something like that. That's a big deal in cellular communications, mobile communications. So just tossing out lots of these things for your background knowledge, right? So up until now, we have not talked very specifically about the symbol shape, other than some examples where it was rectangular, right? We've also not limited the bandwidth of the channel, but reality dictates that practical channels are band limited. Even a fiber optic channel is band limited. Fibers have really wide bandwidth, but obviously it's still finite. But it's really the detector and the emitter, the light emitting diode or laser at the transmit side, or the detector where you're sensing the light, that's going to have a finite bandwidth and limit your channel bandwidth. So all channels are finite in nature, finite bandwidth. So we can view that channel as a filter with the impulse response H of T, or corresponding spectral response of H of S. So we're going to look at that as basically a bandpass filter, or in some cases, or some perspectives, a low pass filter. Okay, so I don't think I'll go any farther here. Spent all my time on the preview, test preview, and going over the homework. So, but we'll talk about intersymbol interference. The other thing we've kind of been simplified on is that we've looked at one pulse, but really to communicate, we need to send a whole bunch of pulses one after another. And we'll find out that we need to worry about the effects of one pulse on another, and that's called intersymbol interference. All right, so I'll have my office hours on Monday. I think people have told me that that's a tough time for them to make, so please send me an email if you need another time. Like to get y'all thinking about getting to office hours before the day before the test, but I'll be available on Monday. So all right, have a great weekend.